All right, everybody. So now we're here to talk about matrix multiplication. And there's some certain rules that go into when you can and can't multiply two matrices. But before we get to that, I want to show you how to multiply a row times a column, because that's really the basic thing from which all of this kind of flows. So in order to do that, you have to have that the row has the same length as the column does. So let's say we have a row that's really like n columns long and a column that's like n rows long. Then we can do this matrix multiplication. But what we'll get out of it is a single number when we do row times column. So as an example here, let's say I have this row matrix whose entries are 1 and 2, and this column matrix whose entries are 3 and 4. Then the product of this row times this column will be 1 times 3 plus 2 times 4. That's just the kind of definition here, okay? And so that becomes 3 plus 8, which is just the single number 11. So notice in here that we have a matrix that is 1 by n and a matrix that is n by 1. And we get out a matrix that is technically 1 by 1, just a single number. Okay? And so now let's think about larger matrices. So for just two general matrices, A and B, the product A times B is only defined when the number of columns of the first matrix A equals to the number of rows of the second matrix B. And when you do this, then the number in the ith row and jth column of A times B is exactly the number that you obtain from taking the ith row of A and the jth column of B and forming their row times column product this way. Okay. And so, so there's this kind of clever way you can check to make sure that your matrix product is defined. So here I've got this matrix A and this one B I've labeled on the right. And notice that A is 2 by 3 and B is 3 by 2. And so the stipulation for the product to be defined is the number of columns of A must equal to the number of rows of B. So in particular, it's these two kind of like inside numbers here. So 3 and 3, they match. So then the product A times B is defined. And I guess I should probably say this now. When this is defined, its size, the size of the product A times B is going to be these two numbers left over here. So we'll have 2 rows and 2 columns left over. Okay? So in the first row, first column of A times B, we'll take the first row of A and the first column of B, and we'll form their product that is 1 times 3 plus 3 times 7 plus 4 times minus 1, which gives us 20. Okay. For the first row and second column of the matrix A times B, we will take the first row of A and the second column of B and form their product. That gives us 1 times 5 plus 3 times 9 plus 4 times minus 2, which turns out to be 24. Okay, now for the second row and first column of the matrix A times B, we'll take the second row of A and the first column of B and form their product. That gives us 2 times minus 1, or sorry, 2 times 3, sorry, plus minus 1 times 7, plus 7 times minus 1. Okay, and so this gives us then, let's see, minus 14 plus 6 is minus 8. Good. Okay, and then for the second row and second column entry of the product A times B, we will take the second row of A and the second column of B and form their product. This gives us 2 times 5 plus minus 1 times 9 plus 7 times minus 2, which turns out to be minus 13. So the matrix product A times B looks like this. Okay. Let's see another example here. They've given us a 3 by 3 matrix and a 3 by 1 matrix. Notice that the number of columns of A matches the number of rows of B. So the product is defined. And the product will be a 3 by 1 matrix. So that will be 3 rows, 1 column. Okay, so then for the first row, first column, we get 1 times 2 plus 3 times 1 plus 2 times minus 2. And that turns out to be 1. Okay, for the second row, we get 2 times 2 plus 1 times 1 plus 3 times minus 2. That turns out to be minus 1. And for the last row, we get 4 times 2 plus 0 times 1 plus 5 times minus 2, which turns out to be minus 2. Excellent. Okay, a couple more examples here. Notice this matrix here is what? 1 by 2, and this second one is 2 by 1, so the two inner numbers match. And the result that we're going to get is going to be a 1 by 1 matrix, just a number. So we've done this now, we've seen this a bunch of times. This is just a row times a column. So we get 1 times 5 plus minus 1 times 6, which gives us minus 1. And so if you really, I guess if you wanted to write that as a matrix on the nose, you could write these little kind of brackets around it. That's fine. I don't know how Connect Math is going to care. We'll see when we get there. Okay, but then this last example is kind of nice because it takes the previous example and interchanges the order of the two matrices. And let's wonder first, can you even do the product the other way? Well, luckily, the first matrix is a 2 by 1, and the second matrix is a 1 by 2, so those inner numbers are going to match 1 and 1. But now the product A times B is going to be, I really probably should have, sorry. I really probably should have written B times A for this one if it's referring to the previous example, but that's fine. So now the product here is going to be a 2 by 2 matrix. Oh, okay. So it looks like the first row of A times the first column of B is just 5 times 1, which is 5. Okay, the first row of A times the second column of B is just 5 times minus 1, which is minus 5. The second row of A times the first column of B is 6 times 1, which is 6. And then the second row of A times the second column of B is 6 times minus 1, which is minus 6. So notice here that if we multiply these two matrices in opposite order, we get completely different answers, right? And in fact, there's sometimes where you can do a matrix product in one order, but if you turn it around, then the inside numbers won't even match, so it won't even be defined the other way. So there's actually deeper problems than just this one. So together, this really shows, though, that what matrix multiplication is not what they call commutative. So it does not satisfy this kind of nice property of numbers that generally like A times B equals B times A. That is not going to be the case for matrix multiplication. All right, but that about does it for that. So stick around for the last talk that we'll do, which is about finding the inverse of a matrix. It's this idea of, now that we've got multiplication on there, is there a way to do any kind of division by a matrix? Well, not all the time, but sometimes yes. And so we'll kind of visit that in our last talk next time. See you then.